Hey everyone, it's Jay. I want to kick off our discussion of diabetes mellitus by talking about how blood glucose is normally regulated by the hormone insulin. If we want to talk about insulin, we have to know where the pancreas is. The pancreas is an organ in the abdominal cavity that's associated with digestive activities as well as secreting hormones like insulin. So we can remove the digestive organs here, zoom in on the pancreas, and when we look at the tissue, you see that the majority of pancreatic tissue is involved in digestion. There are these small islets of cells called pancreatic islets, and they're involved in secreting a number of different hormones. One of them is insulin. There are special cells in the islets called pancreatic beta cells that secrete insulin when blood glucose is elevated. Humans need to maintain blood glucose homeostasis to stay alive. Normal blood glucose levels are about 70 to 100 milligrams per deciliter. If glucose levels fall below that, our brain stops to work. And when glucose levels increase above that, the glucose will attach itself to proteins in the body and disrupt the structure and function of cells and tissues. We'll have the complications associated with diabetes mellitus that could eventually result in death. So today we're going to be talking about what happens when glucose climbs after we eat. The initial change then is an increase in blood glucose. So we've eaten a bowl of Lucky Charms. The glucose travels through the bloodstream and will enter pancreatic beta cells. So pancreatic beta cells serve as both the sensor and control center in this feedback loop. The beta cells are special in that they always have glucose transporters in the cell membrane. So as blood glucose increases, there's increased glucose traveling into the pancreatic beta cells. The increased glucose entry into the cells will cause insulin release. So this is going to increase ATP in the beta cells, and that will cause the release of insulin. Now, insulin will travel through the bloodstream to target tissue that includes the liver, skeletal muscle, and fat. Now, the liver is critically important. I'm still going to just cross it out for now because it behaves slightly differently than their simplified model. But we'll say without insulin, glucose can't enter skeletal muscle and fat cells. So without insulin, glucose can't enter cells. There is no glucose transporter. When insulin binds to its receptor on target tissue, it causes glucose transporters to be inserted into the cell membrane of the cells, the skeletal muscle and fat cells. So insulin causes GLUT4 glucose transporters to be inserted into the membrane of effector tissue. So once glucose transporters are inserted into the plasma membrane of the skeletal muscle and fat cells, there's a concentration gradient that moves glucose from outside the cell into the cell. Glucose enters target tissue. So the response then is a lower of blood glucose and a return to homeostasis. All right, so this is a good thing. We can stay alive. Quick summary. Humans have to maintain blood glucose homeostasis to stay alive. Glucose climbs after we eat a meal. The increased blood glucose enters pancreatic beta cells. Glucose can always enter those cells, and this causes the release of insulin. Insulin travels through the bloodstream, binds to its receptor on target tissue, including the liver, skeletal muscle, and fat. In skeletal muscle and fat cells, insulin binding to its receptor causes GLUT4 glucose transporters to be inserted into the plasma membrane of those cells. As soon as they're there, there's a concentration gradient that drives glucose from the blood into the cells. As glucose leaves the blood glucose drops, and there's a return to blood glucose homeostasis. This is the feedback loop that we need to know before we start. It's the one that's broken in diabetes mellitus. So we'll move on in the next video and talk about how that happens.